So Professor Russell Cowburn, who's speaking today, is a professor of nanotechnology at Cambridge, but he seems to have travelled the world before that. He's worked in CNRS in Paris, Durham and Imperial. I suppose actually that's not quite the whole. Some important parts of it. And he's won lots of awards for the link between science and technology. And he's got 60 patents, but he's also top of his field in science. He's a fellow of the Royal Society. So sitting at a very interesting place between those two, and has been working on very small things. I think his title is The God of Small Things, and that's what he's going to talk about today.
Wonderful. Great. Well, thanks very much, Bob, and thank you very much indeed for coming. So, what I'd like to talk about tonight is the God of small things, nanotechnology, creation, and God. And so I'm coming at this as a professional nanotechnologist and also as a practicing Christian. And I guess I've been doing both for similar lengths of time. I became a Christian at the age of 18, just before embarking on a degree in physics. And so I guess the apparent tension that people think exists between science and faith is something that I've been living my entire life. So hopefully I can point to one or two things that I found out along the way. So here's what I've got. I'm going to give you a quick primer on nanotechnology. So by the end of this, you will all be set to go off and become budding nanotechnologists. I'm then going to answer the question, why bother? What's exciting about nanotechnology? I then want to talk about what's terrifying about nanotechnology. And then finally, what does God think about it? And more generally, how do we go about trying to work out what the mind of God is when it comes to new technologies? What is it we're meant to be doing? Is it a good thing for people to be doing technology, or actually is it a bad thing? So, what is nanotech? I'm sure many of you have come across these ideas before, but let's just whiz through this. So, if you think of a size scale with a meter at the top, then we all know what a meter is. That's you and me, the order of a meter. If you go down 3 orders of magnitude to the millimeter scale, then we get to paper clips, and again, we all know what a millimeter looks like. If you then go down a further factor of 100, then you're into a length we call about 10 microns, and at that size scale, diameters of human hairs and dust mites and things like that are the relevant descriptor. So that's a little picture on the right there of a pinhead with a human hair and a dust mite all gathered together. While we're doing sort of human living things, red blood cells are just a little bit larger than 10 microns or so. And then at the very bottom of that scale, if we think of what's the smallest thing that we could realistically handle outside of environments like CERN and places like that, then we think of a single atom. And a single atom is 0.1 of a nanometer, where a nanometer is a 1,000 millionth of a meter. So there are 10,000 million atoms in a meter. Nanotechnology occupies this band here. So it's essentially everything larger than a single atom and going up to a size of about 100 nanometers. And just to give you an example of the sorts of things that we find there, here's one of the earliest experimental results of nanotechnology. It's an abacus. It was made by IBM in Zurich. And you can see how the beads have been moved in order to count from 1 to 10. The only thing that's unusual about this abacus is that the beads are made of single molecules. And you can both image the single molecules and you can move them around in order to make the sliding beads. And that's nanotechnology. So let's just look briefly at some of the techniques of nanotechnology. How do we do that? How do we see things on that size scale, and how do we make things that are that small? And there have been a few technologies that have really driven this field. And probably the most important is that of atomic force microscopy, or AFM to its friends. And it's a brilliantly simple idea. It's a bit like Wikipedia. It's one of these things that works in practice, but not in theory. And if you postulated the atomic force microscope, an engineer somewhere would tell you that'll never work. You'll never get your tolerances right. But actually it does work. And what you do is you take a sharp point, something that's been sharpened to a few tens of atoms in final radius, and you connect it to a spring, which we call a cantilever, and you scrape it across the surface. And as you scrape it across the surface, that sharp point goes up and down along the corrugations of the surface. And if you can measure that displacement as it moves, you can map out the surface, a bit like a blind person reading Braille. So the trick is, how do you measure such small displacements? Because of course that tip is only going to be moving by a few atoms as well. And the brilliant thing that engineers and scientists did in the 1980s was to recognize that if you shine a laser beam onto the back of the cantilever and then move a large distance away, possibly meters away, then very small movements in the cantilever will lead to very large movements in the reflected light. If you imagine, if I shine a laser beam off a mirror and beam it to the other side of Cambridge, if I move that mirror ever so slightly, on the other side of Cambridge, you'll see the reflected laser spot moving by relatively large distances. There's an intrinsic amplification by the length that the light has to run. And you can use that amplification in order to be able to see atomic scale and even subatomic scale displacements at the tip, and so you can map out your surface. There's a sister technique called scanning tunneling microscopy, which has been equally important. And together, they are both the eyes and the hands of nanotechnology. They allow us to see things and they allow us to move things. And just to give you a little flavor, there's a surface of some silicon atoms seen through one of these scan probe microscopes, and you can see the little rings that the atoms of silicon form into, a structure that you don't see in the bulk of it. So already there's interesting science to be found, that surfaces are different to insides. If you go into my lab, and in fact this is from the Cavendish, you would soon stumble across this sort of thing. One of the ironies of nanotechnology is that the smaller the stuff you want to look at, the bigger the machines you need. And so my lab is full of stainless steel pressure vessels, and this is just one such example. And this is for the creation of very thin layers. A lot of this work has to be done in very high levels of vacuum, so that a passing air molecule doesn't bash into your surface and destroy the thing that you've just made. And so we pump these things down to levels of vacuum comparable to what's found in outer space. And that allows you then to work in relative tranquility without atmospheric molecules bouncing off your surface too frequently. And in this set of chambers, we would do a technique called sputter deposition, which is a bit like if you boil potatoes in a cold kitchen, you'll notice a layer of moisture on the ceiling. That's essentially what we do. We heat a lump of metal up to a point close to its melting point, and we allow the vapor to drift up and then to recondense, usually onto a silicon wafer. And it forms roughly atomic plane by atomic plane. So the longer we leave it there, the thicker the layers that we get. And we can control that with subatomic thickness resolution. So we routinely put down films that are just a single atom thick using these sorts of methods. And then an equally important method is electron beam lithography, where we run an electron microscope back to front. If you've ever picked up a telescope or a pair of binoculars and looked down from the wrong end, you'll know that something designed to make things look bigger can equally well be used to make things look smaller, just by running it back to front. And that's no exception with an electron microscope. And of course, because the electron microscope is very good at making things look very big, it's also very good at making things very small. And so we program the electron microscope under computer control to draw the shapes that we want. And it will draw them with a resolution of a few tens of nanometers. And with a chemistry process, we can convert places where the electron beam has been into real physical material. And this allows us to actually build things on the nanoscale. To give you a little feel for that, here's, this is back from my student days. It was a Friday afternoon and we were a little bored. And we decided to try and copy out part of the Encyclopedia Britannica onto a piece of silicon. For those of you under the age of 35, that's what we used to call Google. But, the idea is you can use pen strokes that are just a few tens of nanometers, and at that density of writing, you could copy the entire Britannica into a page of A4. So those are the techniques. Let's look briefly at some of the materials of nanotechnology, and materials are very, very important. It's not just the techniques to manipulate things, but it's actually the stuff that we work with is where a lot of the excitement is. And carbon has been very good to us. When I was a schoolboy, I was taught that carbon came in two forms, diamond and graphite. And now we know that there are three other forms. There's carbon-60, which was discovered by Harry Kroto, won the Nobel Prize in '96. And these are little footballs of carbon molecules with 60 carbon atoms making up the little football. There's carbon nanotubes, which are sheets of carbon atoms arranged like chicken wire, rolled up into a tube. And then there's the single unrolled form of that called graphene, which I'm sure many of you have heard of. There's a Nobel Prize, again for the UK in 2010 for that, where you just have a single plane of graphite arrangement, these little hexagons. And all of these would be what we call nanomaterials. So what's exciting about nanotechnology? Why should we go to all the trouble and the expense of using these big machines and handling these exotic materials? What's the reason for doing this? Well, we can describe what we call the nano advantage. And it's very simple. The nano advantage is very simply the properties of materials are different on such a small scale. And I really want to stress this. Sometimes people think nanotechnology is just more miniaturization for the sake of it. Every year things seem to have to get smaller, and so nanotechnology is just the next step in that process. That's absolutely not the case. The reason we go small is because we can do things on a small scale that we wouldn't be able to do on a larger scale. New properties, almost, I want to say, new laws of physics. I don't quite want to go that far, because it is still one encompassing set of laws of physics, but it appears from the outside as if the laws of physics are dramatically modified when things are so small. And with that new set of properties that we get, we can hopefully build things that are better, that are cheaper, that are smarter, that are cleaner. That's the narrative, that's the nano advantage. Let me give you just a few little examples of that. So in the world of computing, this is the first transistor. This is back from 1947, the original transistor. This thing's a museum piece. It's about that big for a single transistor. And you can really see the individual bits of, I suspect, germanium rammed into each other, and then electrical contacts made to them. Scroll forward half a century, and that is a transistor today. And if you look at the size, the length scale on the left-hand side, you see the width of it is 65 nanometers. And interestingly, it's largely the same underlying operational principles as those enormous transistors of the mid-20th century. We've pretty much unchanged how it works, but we've just shrunk everything step by step, year after year, for half a century, and now we end up with something that is definitely nanotechnology. And in fact, this slide is probably 5 years out of date, and I think probably the modern slide, today's slide, would have 32 nanometers written there, and next year it'll be 28, and on it goes. And the reason we want to make them so small is to be able to get more of them for the same price, which largely means we can make stuff that is smarter, that's more intelligent. I know often people say, I don't want a more complicated computer. My computer is already complicated enough. I don't want any more transistors in there. If anything, I want fewer transistors. But I really beg to differ. The reason you find your computer so frustrating is because it doesn't have enough transistors, which means it doesn't think like you. And that if we can get more processing power, more memory, more intelligence into these things, then they will become more the way you want them to be, rather than the way that they have to be. Healthcare is another area to have benefited enormously from nanotechnology. So here's just an example of some work from a colleague of mine back at Imperial, Rachel McKendry, where she's using the cantilevers, the springs of the atomic force microscope as a super sensitive thermometer. So sensitive that she can measure tiny packets of heat emitted by chemical reactions between very small number of molecules. So she actually uses the cantilever as a laboratory where she does her chemistry with built-in temperature measuring capability. And in this work, she's investigating the hospital-acquired infection MRSA and trying to work out what is it about MRSA, what's about the chemical structure of MRSA that makes it immune to antibiotics, for example, when other bugs are blasted relatively efficiently. And it's those sorts of studies that link the chemical structure to the immunity or to the properties that ultimately lead to cures for these sorts of infections. Renewable energy is another area that's enormously important. And again, here's just an example of some things from my former employer, Imperial College. They use use three materials: gallium arsenide phosphide, and indium gallium arsenide, all of which are relatively similar, and yet none of which by itself makes a particularly good photovoltaic. And this is a huge issue. If you work out how much energy lands on the roof of your house from the sun, it's plenty compared to what you actually consume indoors. We do have enough energy coming to us. The problem is we just can't capture it efficiently. And so we need new materials that are more able to capture all the energy coming from the sun. And one of the ways that nanotechnology helps there is by modifying the ability of materials to capture sunlight. So in this case, by growing atom by atom a sandwich of these three materials, you end up with properties that none of them individually has. You stretch the atomic spacing and you give the electron wave functions new abilities to catch sunlight. And so they've been making highly efficient solar cells. I think the little test devices you see on the side of a 10p piece there have about a 48% efficiency of converting sunlight into energy. So there's the good news story. That's all the nice bits. What about the nasty bits? What's terrifying about nanotechnology? Why is it that when I visited Clarence's house last year, my colleagues advised me to keep quiet in Prince Charles's presence? I was a nanotechnologist. Why should I want to hide this good news story? Well, let me give you a little bit of history, because the history is quite fun, and it's a great example, actually, of how misunderstandings can arise. So in 1992, there was a very interesting book published by a chap called Eric Drexler called Nanosystems, Molecular Machinery, Manufacturing and Computation. And it was basically his PhD thesis from MIT that he published. And it was a very far-reaching work. Back in the early 90s, when nanotechnology was very much in its infancy, he began to ask really basic questions about how do we make things? What stops us from making things at an atomic scale in a completely different way to the way that we do today? So it was very futuristic work, a very serious piece of science, but it was well ahead of anything else that was going on at the time. 10 years later, Michael Crichton, the author of Jurassic Park, published a book called Prey. The important thing to spot in the picture on the right-hand side of this slide is there's very small words in the middle, a novel. And that's really important. The left-hand one is a PhD thesis and is very serious. The right-hand one is a novel and is extremely entertaining, but is no more than that. Let's just dip a little bit back into the Drexler work, and then I'll tell you more about Crichton. So what Drexler postulated was something called a universal replicator. And actually, it's easier for us to imagine something like this. This is an artist's mock-up at the top. Nobody's ever built such a thing, but this is the mock-up. And it's pretty much what we would think of today as a 3D printer, except with atomic resolution. So his idea was to say, well, on the left-hand side of this machine, we'll have feedstocks of really basic chemicals, methane, hydrogen, very simple molecules, or even atoms. And inside, we'll have an amazing Charlie's Chocolate factory of belts and pulleys and cogwheels and grabbers and all sorts of things that will strip those atoms apart and bang them back together again, atom by atom, and will construct from the bottom upwards anything we want to make. And if you do that intelligently enough, you've got all the basic stuff of manufacturing. You've got carbon, you've got hydrogen, nitrogen, all the basic atoms that stuff is made from. You could build anything. And he then went on to say, well, what if we choose to build a machine that can build other machines? And could we then create a whole manufacturing plant that could replicate any item we choose and indeed replicate itself? And this would be a completely new strategy for atomic scale, bottom-up manufacturing. And then really as a final chapter, he then very responsibly addressed the question, well, what if it escapes from the lab? What if this thing gets out and eats, I don't know, you or me, and starts to use us as its feedstock, and starts to disassemble us and rebuild us into other things, and specifically other machines that eat people and convert them into objects? What would we have then? And quite clearly, we would no longer have a manufacturing product, we would have a plague. And the ultimate extension of this nightmare scenario is that this swarm now of replicating machines eventually eats the planet and converts everything in its path into so-called grey goo. And that's the phrase, that's where the phrase came from, this idea of reducing objects of useful feedstock into useless sludge, essentially. What didn't help was then Crichton's novel, which basically described the same scenario and described a plague of out-of-control nanobots. And in the public mind, these two things have become a little bit confused. And so, for example, a wonderful Daily Mail headline a few years ago, grey goo food laced with nanoparticles could swamp Britain. The underlying story is the idea of putting little engineered nanoparticles that contain fortified nutrients, be it extra vitamins or whatever, into food in order to make it healthier, just in the way we add things to breakfast cereals, toothpaste or water, all these sorts of things. And if you can carry them in little nanoparticles, they can be absorbed more readily, and you can do things that wouldn't get through the stomach acid of other nutrients. The trouble is that very laudable and very beneficial idea has been conflated with the slightly science fiction idea of particles that can self-replicate, that can eat material they find in their way, and that can turn you, me, and the rest of the planet into grey goo. Of course, they were never meant to be conflated. These are very different things, but in the public mind, there's a degree of confusion. So much so that even just a few weeks ago, Dunkin' Donuts ran into trouble. I don't know if you saw this. This was reported in The Guardian and in quite a few other places, where the pressure group, who are actually shareholders, did some analysis on the white coating on American Dunkin' Donuts. It's a different recipe in the UK, so you can relax. And found nanoparticles and made a shareholder's request to the company that they should withdraw any produce that contains nanoparticles. Dunkin' Donuts' response has been, well, we don't use nanoparticles. These aren't nanoparticles. What they actually are is food-grade titanium dioxide, which is actually an extremely common agent. It's a whitener. It's relatively harmless. There's no evidence that it does anything bad. And you find it in everything, in toothpaste, in bread. Anything that looks vaguely white is just given an extra little polish to make it just slightly whiter with this titanium dioxide. Now, of course, what happens is when these particles are synthesized, which aren't trying to be nanoparticles, there's no benefit to putting nanoscale particles as a food whitener. You obviously end up with a distribution of sizes, and there will be some particles that just by chance end up being smaller than the 100 nanometer threshold at which nanoparticles are efficient to find. And we think that's what happened here. And so Dunkin' Donuts has basically said, well, we don't need to use these. We're not trying to do anything particularly nano. We will very happily withdraw them and find something else instead. But I thought it was a very nice example of how the fear that is attached to nanoparticles can be confused with relatively well-understood food additive issues. We know food-grade titanium dioxide as E171. We may choose not to eat it, but it's just another refactor as far as most people are concerned. Okay, so there's the terrifying part of nanotech. Let's now turn to a little bit of theology and just try to address this rather grand question: what does God think about all this? I'm going to speak about this as a Christian. I am a Christian, and so I'm going to bring a Christian perspective to it. And I'm going to start with a broader Christian view on technology in general. And I find the opening verses of the Bible actually a great place to try to work these things out. So the opening chapter of Genesis says, "Then God said, let us make man in our image, in our likeness, and let the rule of the fish of the sea and the birds of the air, over the livestock, over the earth, and over all the creatures that move along the ground." So God blessed them and said to them, "Be fruitful and increase in number, fill the earth and subdue it." And a very simple textual analysis of that tells you there are two contrasting strands in there. There are a number of words to do with control: rule, fill, subdue, overall the earth. So I take from that it is fully permissible to engage in technological activity that attempts to subdue the earth. We are given the remit to rule. We are not equal passengers amongst all other animals on the planet. We are given a specific mandate to use technology, to use science, in order to shape the environment as we think fit. But in addition to that, there's these phrases, in our image, in our likeness, which I think is a modifier to this mandate to control and rule. And essentially it says we may not be equal passengers, we may be the ship's captain, but we're not the overall boss. That any rule, any subduing, any filling that we do has to be in the image of God, in the style, in the likeness of God. It has to reflect the way he would do things. And if we fail to do that, then we are not fulfilling the mandate we were given in how we should rule. And so I would say that to rule in God's image means our technology has to have good ethics and it has to have good theology. We have to be doing the right things. It's okay to do things, but we have to be doing the right things, and we have to understand how those things stand in relation to God. So let's just look at both of those. Let's look at the ethics and the theology of nanotech. So the first really important ethical implication is that of safety. It's quite clear that if what we do isn't safe, then there is no sense in which that's us ruling in God's likeness, in his image. We have to look at the balance of the risks to the benefits. Specifically, are the risks disproportionate to the benefits? There's no point in doing things that are crazily risky if it's just to make donuts a bit wiser. And I don't quite know how to interpret the result of the question, but I think it's right to ask the question, are similar processes used in nature? I think as part of the ethical assessment of nanotechnology, I want to know whether what we are doing, is this the first time it's been done on the planet, or actually has nature been using similar processes already? So let's just look through those briefly. Let's look at safety first. This is how we tend to assess safety of nanotechnology. We plot a two-dimensional axis, and on the bottom axis we look at the quantity of nanomaterial, how much nano stuff are we talking about, and up the vertical axis we look at how accessible to people largely, but to other animals as well, is the nanomaterial. So on the quantity, it might be nanograms or it might be kilograms. And on the accessibility, it might be bound, in as much as not accessible at all to us, or it might be completely free and absorbed entirely by the human body. And I've just put 5 different regions in here, just to give you an example of the different way these two axes balance out. So at the bottom left, you've got microchips, those transistors that we saw that now fill our mobile phones, our laptops, our tablets. And there are billions of transistors in those, but actually the total amount of nanomaterial is still relatively small. If you cracked one open and scraped all the transistors off and weighed them, it would be hundreds of nanograms of total material. And the transistors are firmly bound to a silicon substrate. They're not floating around in the air, you don't breathe them in, they are absolutely an integral part of the solid structure. So that would put microchips as the safest part of nanotechnology. If you go vertically up, we still stay in a world of relatively small amounts of material, but now increasingly exposed to people. A nice example of that is at the top, of magnetic resonance imaging contrast enhancement agents. So at the moment, if you are suspected of having a brain tumour or something else where people want to do MRI scanning, they'll give you some form of gadolinium in order to show up different types of tissue and different problems. There are thoughts, there are ideas that we could be much more specific. We could really highlight tumours or highlight very specific medical conditions if we could use something slightly smarter. And so people have tried to use other types of nanoparticle that would be more specific, that would only light up for certain conditions. So what would the safety of those be? Well, they'd be in the top left-hand corner, relatively small amounts, but now fully accessible. You'll be given a drink, or they'll be injected straight into you. The bottom right, we've got things like nanofibers, which are used for making everything from better raincoats through to surgical implants and skin grafts. And there, these are relatively large amounts, but they're not being absorbed. The danger area is in the top right, where there's lots of stuff and it's right inside you. That's the area where we need to be most careful. But I would stress, we don't need to worry about grey goo. It's not that these things are going to burst out at you and start consuming the rest of you and then the rest of us. It's much more a standard toxicology approach. We want to be sure that they don't trigger other chemical reactions, that they don't get stuck inside us. In other words, for nanotechnologists, the Armageddon scenario is not actually grey goo. the Armageddon scenario is asbestos, something that we think is a good idea, but which actually turns out to have unanticipated health consequences. I leave in the middle there sunscreen, which is another interesting application, where I think actually the safety issues are a little more pointed, because actually there are relatively large amounts concerned, and it is not exactly absorbed, but it's free. You do splash the stuff all over you. And just to keep with our donut theme, that's where I would put the Dunkin' Donuts. Again, not huge amounts, and not particularly absorbed, and we're fairly certain the same dioxide is pretty harmless anyway. Let's just return briefly to the sunscreen, though. There was some very interesting work published out of the Spanish National Research Institute last year, which looked at the consequences of sunscreen on beach users at seaside resorts in the Mediterranean, washing off and ending up in the sea. And they concluded that there's about 4 kilograms of titanium dioxide nanoparticles put into the Med every day on a beach resort, just through greasy swimmers. And what are the consequences of that? And one of the surprises, it seems that those small nanoparticles, and indeed larger microparticles of titanium dioxide, can, under ultraviolet radiation, can catalyze the formation of hydrogen peroxide, which in turn is toxic to plankton that fish feed on. And so even though we're not concerned about our grey goose scenario, we do have to look very carefully at the whole chain of toxicology and make sure that we're not inadvertently poisoning fish through these sorts of things. And there are similar concerns about nanosilver that is used in socks in order to make them smell fresher. But of course those socks then go through the washing machine, and some of the nanosilver comes off and ends up in the watercourses, and ultimately ends up in the rivers, and the fish eat it, and we have to worry what effect these things have on wildlife. So what about the balance of risk? How do we compare the potential benefits to the potential risks? Well, that's going to be a dynamic calculation. It'll always be changing. But I think at the moment we need to be very clear that a number of the global challenges, the things that are on top of people's list as the greatest threats to our planet, are things that nanotechnology has potential solutions for. So we've talked about global warming and how engineering materials can change their ability to convert sunlight into energy. Water availability. You can make some great natural filters out of highly porous nanomaterials that could allow you to clean up polluted rivers, or that could allow you to convert salt water into drinking water. Limited material resources, finding new ways of creating smart materials. A great example of that is mobile phone touch screens. Up till now we've used indium tin oxide as the material to coat touch screens with, largely because it's the only material we've got that's both transparent and conductive. But the world's running out of indium. Graphene seems to do the same job, and so I don't know if it's in the market yet, but very soon we should have graphene-covered touch screens. And on we go: energy security, aging population, drug-resistant infections, we talked about that, terrorism, and access to the developing world to IT. These are all big global issues to which there are really interesting and potentially very potent technological solutions available. And so we have to balance these against these toxicological risks that are usually associated with any new material, and make sure that we come up with a sensible balance between risk and reward. Let's just look at this other ethical question now of nature and nanotechnology. Are we the first to get there, or actually is this stuff out there all around us? Just a couple of examples that might surprise you. If you go to South America, one of the things you'll see flapping around is the morpho butterfly. It's a very beautiful butterfly. It's particularly beautiful because of its blue iridescence. And what's interesting is the blue colour that its wings have doesn't come primarily from a pigment, but actually it comes from built-in nanostructures in the butterfly wing. If I zoom in on a wing, what you see are these very carefully ordered arrays of nanostructures that diffract light at just the right wavelength in order to give you this blue iridescence. We call this structural colour, and it's found elsewhere in nature as well. We don't have to go to South America though, we can find it here in this very room. The very thing that drives metabolism, the biological process that gives us all life, is the conversion of adenosine diphosphate into adenosine triphosphate through an enzyme called ATP synthase. This is the rocket fuel of life, and it powers all living processes. And when you look at the proteins that make up ATP synthase and how they operate, it's actually a little nano machine. It's a little motor. You've got a stator part that stays still, and you have a rotor part that spins on a bearing. And as it spins, it strips protons and phosphates and pushes them together, and out comes ATP to then go on and drive the rest of the metabolism in all our cells. From an evolutionary point of view, ATP synthase is very, very old. This seems to have been involved in life since the very start, long before anything as advanced as humans or even our predecessors. So from the very start, life has been powered by nanotechnology. So it seems that it's definitely not a new thing that we've done. If anything, we're late to the party. They're only just beginning to catch up. So finally, what are the theological implications of all of this? So I've got three different things to look at, and then I shall stop. So the first is a question, and that's, is nanotechnology potentially implicated as the missing link in abiogenesis? Now don't worry, I had to look at abiogenesis as well. So modern science has a fairly good picture that pieces together the origins of us, of animals, of plants, of life as we know it, pretty much all the way back to the Big Bang. If you listen to any of Brian Cox's programs, you'll hear him use this very memorable phrase that we are the nuclear waste of stars. We understand how from the Big Bang we can create very simple elements like hydrogen, helium, how they can fuse together to make bigger atoms like carbon and nitrogen. And then chemists can just about tell us how those individual small atoms can then form larger molecules, things like amino acids. If we come in from the other end, we know from our science of evolutionary biology how RNA and DNA and small cells can replicate and form, ultimately evolve into more complex species and ultimately us. So we've pretty much got a chain there, all the way from Big Bang right through to you and me. But if we were to go into that chain and look in detail and say, well, which parts of the science have we really nailed, as opposed to those bits that we're a little bit hand-wavy about, it would look something like that. We know from Big Bang to elements, since experiments by Miller and Ulrey, we know how to get from elements to amino acids. What we don't know is how to get, in detail at least, how to get from the small amino acid molecules through to macromolecules like RNA and DNA, and to actually the relatively complex nanofactory that are single-cell organisms. We may think of a single-cell organism as being a relatively simple thing, but actually it's not, it's a really complex thing, and we don't know how to get from those really small molecules up to there. One of the things we do know, though, is that the length scale on which those question marks sit is the world of nanotechnology. The question is really, how do I take single atoms and build something more complex? And that's exactly what nanotech is all about. I don't have an answer for you, but I just want to show you one little bit of science from nanotech that may form part of the solution in the future. And that's the idea of nano self-assembly. If you look at the picture on the left, you would assume that that was something that we made in a lab. It seems very ordered and regular. It looks built, it looks engineered, rather than something we might have found under a stone in a rock pool somewhere. The surprise is that this is a relatively natural material. It's what we call a nodic alumina. There was a little bit of laboratory intervention. We passed an electrical current through some aluminium oxide, but at no point did anybody sit down and say, I want the holes to be there, there, and there. The material formed this very highly ordered array of pores under the action of electrical current by itself. And these are on the nanoscale. These ones here are 100 nanometers apart, but we can make things that are much smaller as well. And so we call this whole process of where you build things that appear to be designed and appear to be complex, but actually don't have any top-down intervention. We call this self-assembly. And what's really interesting about these materials is they can act as templates for other things. So for example, if other chemistry comes along and happens to bind to the surface, it will bind in a very regular, ordered way. And that perhaps, given that these materials occur naturally, there is a route there by which a template can be formed that can hold amino acids together, that can hold small molecules together long enough and ordered enough in order to begin to construct the larger and complex structures that we need for RNA, DNA, and cells. We do know that these materials exist. So zeolites, for example, are a class of material which are naturally porous. If you just go into that rock at the top, you will see an atomic structure that looks, as shown in the bottom right, very regular ordered arrays of holes. And so it's not impossible that amongst the class of material of clays or some other mineral, there might just be enough nano order in order to bridge the gap from amino acids up into something more complex. So we might yet find a missing link in abiogenesis. Should that worry Christians? Should that worry people of faith? I just want to use this moment to remind us of the heresy of God of the gaps, because Christians in particular are very quick to make this mistake. Whenever we see a bit of science that's missing, there's always a Christian somewhere who puts his or her hand up and says, "See, I told you it was God." And there's an enormous temptation when you see things like chains of creation with missing gaps to attribute the gap to God. And I really want to flag that is the God of the gaps fallacy, and it is a route to disaster. Partly because the gap gets smaller every year. I'm warning you now that nanotechnology may yet fill that gap, but also because it underestimates the role of God. In my view of these things, I want to say it's all God. The Big Bang, the creation of elements, the creation of amino acids, it's all God's activity, not just the bits that we don't understand. And so I think an important theological implication of this whole area is that we hold back from making the God of the gaps mistake, and don't worry theologically if we do complete that chain and do have a chemical stroke biological stroke physical description all the way from Big Bang right through to life. That would be great. It doesn't threaten faith at all. And as a final point, I just want to draw some comments from Scripture about the things that God says and the things that He creates, and the relationship between those two. So, in one of the Psalms, this is a real scientist's psalm, it says, "The heavens declare the glory of God, the skies proclaim the work of His hands. Day after day they pour forth speech, night after night they display knowledge. There is no speech or language where their voice is not heard. Their voice goes out into all the earth, their words to the end of the world." And so the idea here is that the heavens, and I take by that to mean astronomy, the looking at the stars, looking at the physical creation around us, is in somehow to hear God speak. It's as if the stars are speaking God's words, pouring forth speech. And that same psalm then goes on to say, the law of the Lord is perfect, reviving the soul. The statutes of the Lord are trustworthy, making wise the simple. The precepts of the Lord are right, giving joy to the heart. And so this is more the written word, this is scripture. And so theologians would talk about the first bit, the things that we learn about God by looking at what He's made as general revelation, and would look at the bits, the things that we learn about God from what He's written as being special revelation. And they both have a role to play in telling us about the nature of God. I would put my work in nanotechnology into the first category of these and say, maybe as a result of all the things that we've done, we see those heavens a little bit more closely. We can see the created order in more detail. We wouldn't have known about the internal structure of the morpho butterfly wing without the tools of nanotechnology to allow us to see them. We wouldn't have appreciated the mechanism of ATP synthase without the nanotools to investigate them. And so the theological response to this is to use that information for further glory of God. This is further speech, further pouring forth of speech and displaying of knowledge that we've seen. And there's a similar pairing. If we go to the very end of the Bible, if we go to Revelation 4 and 5, there's a wonderful pairing there between creation and something more theological. So this is the roll call of honor. This is the angels calling out the greatest things that God has done. And it says, "You are worthy, O Lord and God, to receive glory and honor and power, for you created all things, and by your will they were created and have their being." So top of the list of the greatest thing God has done is actually the physical creation of the universe. And If the nanotechnology movement has helped us to see that more clearly, then I think the right theological response is that God should receive more glory, honour and power as a result. That's his action in creation. And then intriguingly, it goes on to say, you are worthy to take the scroll and open its seals, because you were slain, and with your blood you purchased men for God. And this is what theologians would call redemption. This is, the first half is God's action in creating things, and the second half is his action in rescuing and recreating things. Again, held hand by hand, and as the two greatest things that God has done. And so finally, I think I want to end with thoughts of humility and praise, thinking about these things. Psalm 139 sums it up for me, where it says, "For you, God, created my inmost being. You knit me together in my mother's womb. I praise you because I am fearfully and wonderfully made. Your works are wonderful. I know that full well." And I think I want to try to use whatever insights I've gained from nanotechnology in order to be more fearful and to be more in wonder and to see that God's works are even more wonderful than we ever thought that they were. So, I'm done. Let me just remind you briefly of the things that we've talked about. So nanotechnology, it's the art and science of manipulating material on the nanometer size scale, and it's on track to form the basis of the next industrial revolution. The industrial processes that it uses will touch every aspect of our lives, be it from the computers we work with to the sunscreen we wear all day. We really shouldn't worry about grey goo. That's not the place to worry about. We should worry about toxicology. We should make sure it's done properly and it's done thoroughly. No more asbestos. If we get this right, if we handle nanotech properly and we communicate it properly, it has the potential to be a significant force for good, addressing many of the modern global challenges, things that affect both rich and poor. Basic things like where to get water from, where to get energy from. God got there first. Nature is full of nanotechnology. We came in a poor second. And it really doesn't change the basic relationship between science and God. Not now, and not in the future if the abiogenesis missing link is completed. I would argue that it's all God's creative activity. We just see it more clearly than we did before. Thank you.
Thank you very much, Russell. Well, that leaves us plenty of time for questions from the floor. There are 2 microphones here, so if you'd like to ask anything, please put your hand up and speak into the microphone, so then everybody can hear you. So let's start. You're right in the middle, so I don't know which of these gentlemen is going to reach you.
I wondered if you, how worried people actually are about nanotechnology, I guess, in the UK. There's obviously those sort of Daily Mail headlines and I guess Prince Charles, but do you have any insight as to how many people are actually worried about it?
I've got some real data from a few years ago. There was a European Union poll of public opinion across a whole range of technologies taken, and it asked essentially, do you believe technology X would be a force for good, force for bad, or unknown? And it covered things like mobile phones, nuclear power, solar energy, and nanotechnology was put in there. Now, the data are a little bit old. They're probably 10 years out of date now, and so it may well be that things have moved on from there. But certainly, for the data that I'm thinking of 10 years ago, the nanotechnology came out slap bang in the middle. Big fat don't know. Very few people had a strong feeling either way. And that was in contrast to things like genetically modified organisms, where people had a much clearer view that they didn't want this. And yet actually, many similar narratives could have been drawn about potential benefit for the developing world, for example. And so I think the nano community learned that public engagement and communicating things properly is really important. It would be nice to see some more modern data, actually, to see how we've been doing in the last decade.
Thank you. You had a big long list of benefits and potential advantages. I noticed terrorism. What was the link there?
here we go. In many ways, but primarily through new detection technologies. So, in a little bit like the work that I was describing from Rachel McHenry of monitoring chemical reactions by seeing how they influence the nanosystem, you can make, in principle, very sensitive sensors for gas or for biological agents, which can be integrated into chips. And so essentially the possibility of bringing the path lab into a portable device that can detect threats is very feasible. So anthrax is a great example. You know, to detect anthrax, you have to run chemical processes that by the time you've got the result, you're dead. To be able to do those things on a chip in situ would be quite a coup for anti-terrorist operations.
So you can see it sort of being integrated into security systems at airports and that sort of.
Yeah, for example.
Yeah.
For example. Yeah.
More questions or comments? Brian.
Thank you very much. Most interesting and helpful lecture. I was interested in the figures you quoted about the European Commission's analysis of potential threats and extreme dangers. Because, of course, if you look at the Eurobarometer, it depends which one you take, because in terms of GM, for example, one of the most recent reviews from Eurobarometer is that only 30 to 40% of Europeans are against GMOs. There's some 60 to 70% who either don't have a particularly strong view but accept it. So, you know, I think you're right. I think there is a need to have a much more up-to-date analysis of public perception of nanotechnology. But what I'd like to come to in particular is to ask you, how comfortable are you with the procedures that do exist for monitoring nanoparticles? So I'm interested to know how you feel about the toxicology systems that we have. To what extent is this scientists who are self-monitoring, or to what extent is there another regulatory procedure that has been set up to be independent of a scientist's view?
Interesting, thank you. Yes, and thank you for that word Eurobarometer. That was the phrase I was struggling to find. So those data I was quoting were Eurobarometer figures from 10 years ago. So I think it depends largely as to what category the nanomaterial falls into. So if it's a therapeutic agent, if it's a drug, then things, I believe, are very tightly regulated. Indeed, I do some work in trying to use nanoparticles as a cancer therapy, and I'm very interested in magnetic materials. And if you look at most of the work that's gone on in this area, people have chosen iron oxide as the magnetic material to try to use. And from my perspective, iron oxide is a really strange choice because it's a rubbish magnetic material. We've got far better things. The reason people use it is it's officially categorized as a food additive and is licensed for free dispersal. Whereas if I want to use what I think is a better material like cobalt or nickel or something like that, then I've got a much, much bigger regulatory hurdle to overcome in order to get that introduced as a medicine. If it's a food supplement, then it's very different. And if it's something like sunscreen, it's very different as well. And that's why I flagged sunscreen as an area that I think is particularly interesting, because it's on the edge of very relatively lax testing, but it's widely used, and there are very large volumes of this stuff, and you apply it in very close proximity to the body. So I think I'd like to see a little bit more on the toxicology side there. Most of the nanotechnology health risks are exactly the same as would come from any other chemical substance. And so by and large, our approval processes for any chemical are probably the right approach. I think what we need to recognize in the nano world is that things are a little bit more extreme. The particularly small size means the surface areas of volume ratio is greater, and so these things can interact in the lungs, for example, or in the blood much more readily. And so we need to make sure that in testing the chemical, we've also tested it at the appropriate size scale. It's quite possible that a material that we know to be benign in bulk form is more toxic in the nanoscale form. So I think we have to feed that into the testing procedures, as we do. I mean, the Royal Society and others have done a lot on these things in recent years. Increasingly, the regulatory bodies are catching up with the nano dimension of the materials they're being asked to test.
Question right at the back.
Yeah, you talked at the beginning the tension between science and religion, science and your faith, and yet listening to your lecture, there wasn't a moment when your faith seemed in any doubt at all. I wondered whether any of your research or work has actually challenged your faith in God at all.
Interesting question. I don't think my nanotechnology work has. I think in general we feel in this part of physics that we're not working in a particularly tense area. My day-to-day business is largely about small magnets. I don't end up coming into direct conflict with any of the big questions of origin and things like that on a daily basis. So personally, I've never had a moment where something that I've discovered in the lab has led to theological recoil, if you see what I mean. I think there will be other scientists who are also people of faith who are working in parts of science that are closer to the cutting edge, especially those in evolutionary biology and things like that.
Hello, thank you for a very interesting lecture. I just wondered if you are willing to share your own personal definition of God.
Certainly willing as to whether I can synthesize it into a bite-sized response to a question. So I guess my theological position is one to say any being who is by definition greater and more powerful than us can only be known and understood if he chooses to make himself known to us. So I'm looking for revelation as the primary means of getting to know that God. Any God that I get to know or define without revelation of himself is by definition going to be smaller than me because he's a creation of my own intellect. So for something to be greater than me, he has to choose to reveal himself. Personally, I've come to the conclusion that God has revealed himself through the writings of the Bible and through the historical person of Jesus. And that what I see and I read in those two sources tell me all I really need to know about his nature and character. Is that good enough synthesis?
That's wonderful, thank you.
Thank you.
So presumably there are multiple possibilities for revelation. You would agree there are?
Well, I think we've seen here there are layers of revelation. So, for example, I've talked about general revelation versus special revelation. So, although I would look to the Bible and the person of Jesus as the primary place to learn about God, within that, we understand that looking at the stars and looking at the nanoscale tells us something about God, absolutely.
Right, thanks very much. Thank you.
There are just two places.
I feel as though I'm going to lower the tone completely after the previous discussion, but I wanted to go back to the Daily Mail and the Grey Goo. God forbid I should be doing the Daily Mail's job on a day like this, but when you talk about the dangers of nanotechnology, I mean, if we wander back in our imaginations to the 1992 book from MIT that described sort of universal machines or something of the sort, I just wondered whether you did. You didn't talk much about nanobots and stuff like that, or actual machines. I wondered if you perceive dangers in a technology which might fall into the wrong hands, and if there were things that the bad guy could do with this technology. So, I mean, I think of things like nuclear technology where the dangers are clear, but we are sort of preserved from that by the fact it's too expensive for ordinary people to do. Or 3D printers is another thing people have mentioned, and the way you can't do a fat lot with a plastic gun. But I wonder whether this is something which might be cheap and genuinely dangerous. I don't know.
It's an interesting question. I think I would put the risks of misuse, terrorist use of nanotechnology, pretty much into the same category as dynamite and TNT and C4 and these sorts of things. I mean, for a start, all of the energy scales are set by the electron energy. So there are a few electron volts, typically, which means the amount of energy you can release from a nano-type event is the same as the energy you could have released by exploding that same chemical bond. So I don't think we'll be able to make things that are more destructive, at least in terms of raw power, than we've already got through explosives. So I guess the dangers aren't going to be as you know, it's not going to be huge explosions we're talking about. It's going to be something slightly more subtle. Drexler worried about, would it be a synthetic plague? Personally, I don't think it is. I mean, for a start, the universal replicator is still a long, long way off. And I think what we need to remember is that even if such a thing were possible, the objects that it creates are still part of an ecosystem, and they are still constrained by the second law of thermodynamics. They are still constrained by evolutionary and biological competition. I don't see anything in there that would make them any different to you know, any of the other potentially nasty viruses and bacteria that we've already got, Ebola or whatever. In terms of misuse, maybe in the whole area of eavesdropping and privacy, there might be something to worry about there. I don't know if the fly on the wall there is a fly or is actually a transmitting device. No, actually, I think those things come more from, I'm going to pass the buck here to my colleagues in the next door lab, I think they come more from microtechnology than from nanotechnology, actually. Microtechnology is more about making small integrated systems, whereas nanotechnology is more about getting new functionalities out of basic materials. And so I think the little fly on the wall micro-robot is more from the micro world than the nano world. But that is something we will have to think about. As to how we know who's listening and how we continue in the struggle between, you know, vast amounts of information being available through the cloud versus a desire for privacy and then keeping people out from things that they're not supposed to see.
There's a question at the front.
Yes, you talked about seeing the beauty of God's creation at all scales, both astronomers viewing the magnitude of the universe and people like yourself at a very small scale. What can you describe some of the beauty that you see at a very small scale?
I mean, my personal fixation is with a very specific nano object called a domain wall. It's a very acquired taste. There are probably only a couple dozen people in the world that get as excited as I do about this, but you know, we are intense in our excitement about them. And a domain wall is part of a magnetic material, but it's a little self-contained nanostructure that it sort of exists, so we can see them, we can move them, we can even weigh them, they have a mass. And yet they're really just a solution to a field equation. And that really excites me, the fact that it's such a tangible object in some ways, and yet in other ways it's an entirely mathematical construct as well. And I've spent my whole life looking at them and moving them around and making new toys out of them, and I think that's remarkable. And with my theological hat on, I want to say, you know, that should give me one extra reason over everybody else to praise God for the glory of His creation. Because most people don't know just how fat domain walls are.
Can I ask a down-to-earth question, which is under the ethics title here? You said this might be the next industrial revolution. the first industrial revolution was controlled by a few people. They made a huge amount of money. Britain burned actually more carbon than the whole of Saudi Arabia has got under it now. Nanotechnology, you're doing it in the science capital of the world, of Europe, I should say. Certainly one of the science capitals of the world. And you've got 60 patents, and people in control of this technology, maybe can govern what happens with it. What's your ethical take on that? Because we've seen with drugs that drugs are developed in rich countries for rich country diseases, and maybe some of the things that could be addressed easily in poor countries are not addressed. Some of those drugs which might be very applicable to poor countries are not available there because they're too expensive. Now I know Bill Gates and others are doing things about that. But do you have thoughts on how nanotechnology might go, having seen those paths in the past, on the ethical side?
I think it has to be said, nanotechnology is enormously multifaceted, and that helps spreading the ownership. So it's not as if there is a key nanotech patent, or even a key portfolio of nanotech patents that are owned by any particular corporation and too distributed to pin down like that. And so I think that's enormously democratizing the exploitation of it. Is that partly in the biotech industry, but maybe speaking about industry, I know more. That leads to concentration of power is just the scale of the financial capital. If I want to make a microchip with 65 nanometer transistors, I need to spend a minimum. And if I've only got $1.5 billion, I can't get into the game. And so, in the hands of a small number of corporations. One of the things that nanotechnology are new approaches that are potentially less capital intensive. In my world, one of the gold standard fabrication techniques in these $2 billion fabs is called molecular beam epitaxy. This is a way enormously expensive and very few people can afford to do it. I've got a colleague in Bristol in solution can achieve almost the same results. And he calls it, because instead of needing a multi-million-pound machine, he just needs a little bit of solution. So actually there are many cases where nanotechnology allows you very wealthy, big corporations can actually now be done by a startup. So I think that democratization helps even out ownership of these technologies.
I think we'll take one last question. Two last questions, I just saw two hands. One at the back and then one halfway down. How about that? Or the other way.
Also an ethics question. Do you see a contradiction between the role of you as an engineer, the beauty of the creation of God, who wants to help the world with global warming, water, or I don't know, the function, whatever you call it, the human mankind who may just wish to protect what we have without all these things. So should we just preserve what we have and not go into changing it? Because you talk mostly from the position of a scientist who is interested in all these things. Do you have?
I mean, I think at a cultural level, scientists need to communicate the fact that science is part of culture. And is in a similar category to great art or great theatre. You don't think of many theatre goers saying, I can't go to tomorrow night's play because I'm going to the physics lab instead. I mean, these are still slightly two different worlds. And so I think there is a job to be done. And I mean, Brian Cox has been actually bridging that gap quite nicely of helping people to understand science is not about tedious maths, but is actually about wonder and beauty and all of these aesthetic things that form part of what it is to be human, to appreciate them. I don't have to start towards an answer to a question. Maybe we can talk more afterwards about that.
So let's take one last question.
I was very interested in your comment that as you get really small to the nanoscale, you get novel properties that really are not the same as miniaturization of the same things on a larger scale. I mean, that sort of sounds very like emergence, the concept of emergence. Normally, I think in emergence, we tend to think of it as lots and lots of things that get put together and become something bigger and then more complex, and then there are emergent properties coming out of that larger scale, the smaller components. But from the nanoscale, it sounds as if there are things, novel properties that emerge as you get smaller and smaller. Would you be happy about calling those properties emergent properties? Is that something that you relate to in the work you do?
I think I'm very happy to say that nanotechnology is a great place from which to study emergence. So, in my own field, for example, there's some moderately interesting work in something called artificial spin ice, where people take very large numbers, 10 to the 8, vanilla nanomagnets and put them together into a huge network, and they find all sorts of interesting properties in the network as a whole that you wouldn't have assigned to any of the individual structures. And so we would very much look at that in emergent terms. But I think the emergence is, in the nano world, is more to do with as you increase the number of interactions and the number of bodies in the system, if you like. That's where the emergence comes from. I don't see emergence as coming from shrinking per se. I still think that as we shrink, we just change ratios, we make different internal mechanisms come to the fore over other mechanisms, things that are size dependent in a different way, for example, which I wouldn't think of as emergent. I would just think of that as a size dependent property.
Good, that's a good place to stop. Before we thank Russell again, let me just give you a few notices. As I said, there'll be drinks, time to mingle outside in a moment, and a bookstall there. There is a Faraday seminar. We have regular fortnightly seminars in term, and the next one is on Tuesday. And by one of those coincidences, it's by the Professor of Nanotechnology from Oxford, called Andrew Briggs, who's in no way competing with this professor, our very own professor, but you can come and judge. That's Incidentals College, as all our seminars are, in the garden room now, which is just around the corner from here. The seminar's at 1 o'clock, it will be finished by 2. If you come at 12:30, there's a free lunch for that. There is a sign-up sheet if you want to get the monthly newsletters from the Faraday, which just come out once a month by email. You're welcome to sign up for that as well. So it just remains again, so thank you very much, Russell.